Ladies and gentlemen, good morning, good afternoon, and good evening. Actually, good afternoon to most of you. There's a surprising number of Europeans that tune in to these broadcasts live for some reason. I guess the time zone works out to you guys. But anyway, welcome to Geolitix and welcome to the third installment of a series of webinars which we hope will demonstrate the power of cloud processing for GPR datasets. Now, the first one we did was about 6 weeks ago and introduced you to the Geolitix platform, being able to drag and drop data into the cloud platform, being able to position it correctly, process that data, interpret it using either manual or machine learning methods, and then output a 3D model into DXF or into Google Earth. So that was a very quick introduction, and that's all online on YouTube. Our next webinar was done about 3 weeks ago, and that talked about bringing in GPS data into GPR profiles, so being able to position things using GPS positioning. Now, today's seminar, or today's webinar, will be about the use of grids. Now, grids are generally considered fairly easy and standard ways of collecting radar data, but they're deceptively complicated because there's thousands of ways you can do grids, and there's always obstructions, and there's grids that aren't always north-south and at angles and need to be geolocated. So what we'd like to do is show you today how we do that within the Geolitix platform. Of course, as I said, there are thousands of ways of doing it. If we're missing something, by all means contact us if you have a specific use case scenario. While I'm talking, I know that there's a question box on the corner of the webinar screen. I can see it, but just go ahead and start asking some questions. There's a little bit of a time delay here anyway, so it's a lot easier than waiting till the very end. By all means, start asking questions. So let's start with our first project. And this is going to be a very simple project. We're just going to call it grid positioning. And what I've done is I've already uploaded, I think 16 files from, it's GSSI data, but today we're not even going to look at GPR data. I don't care about the GPR data, I care about how we do the positioning. So these are 16 profiles. Very simple, I just dragged and dropped. I'm not going to worry about the velocity. I'm going to use meters just because I'm in Canada. That works for me. I'm going to go to the positioning tab. Now, what we're going to see here is, well, nothing actually. We see one line. In fact, all the data seems to be compressed into one line. Why is that? Well, of course, Geolitix doesn't know what the line separation is. Even if we have a very simple grid, all we can tell is that we know what the trace separation is, so we can figure out the line length. In this case, it's just about 60 meters, but we have no idea how far apart these 16 lines are. Let's go ahead and call it 3 meters, right? So it's a line pattern, so we'll turn this toggle on. It's a line pattern, and we'll say, yep, please make my profiles 3 meters apart. And whoop, there it is. Perfect. So they all start along the baseline here. That's perfect. And we know that this is profile 1, and then profile 16 is at the other end. That all makes sense. Now, let's take a look at these color codes. What you'll see is that there are two colors, actually, or two codes to look at. One is the line itself, which goes from green to red. And one are the dots, or in this case squares, that are at the start and end of the line. So what do they mean? The line itself shows green start, red end, right? Pretty universal. It's the direction that the line was acquired in the field. Okay, so in this case, I know that the guy walked from the bottom up to the top. He apparently walked back again from the bottom up to the top. Simple. Now, these dots, what do they indicate? They indicate what direction you're actually looking at the profiles on Geolitix. And Geolitix is smart because it'll take all your profile data, no matter what direction it was collected in, and reorient everything for you so it always looks in the same direction when you're looking at it on the screen. Why is that important? Well, when you're actually trying to track, for example, a pipe across the site, we might want to be able to go from profile 1 to 2 to 3 and 4, very quickly flick through them and track that pipe along. And that makes it a lot easier to do than if each profile was reversed back and forth. So this is a very quick way of doing that. In this case, they are all going in the same direction. We can see that it goes, the line originally was acquired from the line color, from the bottom to the top, and we're looking at the data in the same direction, from the bottom to the top. So that's great. Now, well, what if they didn't go bottom to top? What if they went left to right? Well, it's pretty simple. We just change this to 90 degrees, bang, done. So now, all the lines go in the right direction. This is line 1, and this is line 16. Okay, and I could put any number in here I want. I could make it 23 degrees. That's fine. Okay, that's cool. Let's go back to 90. But wait a minute, you might say, hold on. I actually started here, but my next line was up here. It's to the left, right? So, well, this is important. It is to the left. So let's think about things in the Cartesian plane. If I am starting at the start line of my first line, at my origin, and my next profile was to the left, it's actually a negative number, right? We're moving in the negative plane. The right being positive, left being negative. So let's go ahead and call it negative 3 meters separation. And there we go. So now profile 1 is at the bottom, profile 16 at the top. Everything makes sense. Okay. So let's go back and put everything just normally, not 33 meters. There we go. Okay, so we're back to our original scenario. Very simple grid. Everything goes from the bottom to the top. That's great in Cartesian coordinates, but who cares about Cartesian coordinates? We probably want to put things in real geolocated coordinates that we can output a KML file or, a cool Google Earth image or something. Well, how do we do that if we're just in an XY plane? Well, we have that built in as well. So what we do is we go to Geolocation, and there's actually 2 ways of doing this. So the numbers that we need are the latitude, longitude of the 0, 0 mark. Okay, that's the origin. And we also need to know either the angle that the entire grid is tilted at, because obviously grids don't naturally go perfectly north-south or east-west, or we need to know another point somewhere along this baseline to the right. So, for example, we use this point and this point, for example. It could even be out here, because knowing those 2 points, we can work out the angle of rotation. So let's start with the first scenario. Okay, we're just going to enter in some coordinates here, which we'll put this, hopefully, in a parking lot in Vancouver, Canada. Oops, 1, 2, 3. Okay, and we're in Vancouver, so certainly northern hemisphere, western. Okay, so now we are in some sort of coordinate space. Now, let's take a look at this. Hey, what happened to my lat long? These are now numbers. That's right, because lat long doesn't actually translate very well to measurements. So what we automatically do is do everything in UTM WGS84, Universal Transverse Mercator WGS84. Now, yep, the guys in the UK are probably going, oh, well, we need, OSGB. And the guys in France are saying, we need the French grid. And the Germans need the German grid. And yep, we're fully aware of that. That's a little bit more complicated to implement, but is something on the timeline and in our roadmap of development for this platform. So we will be supporting world and national grid coordinate systems for now. We're working entirely in UTM, but it's very simple to take something from UTM and translate it into OSGB or whatever state plane you're using in the United States, for example. So here we are. Well, that's all very well, and we now know where we are. Let's go ahead and add a background image. So we'll say, I guess, Mapbox is the first one here. And, oh, here we are. Well, really? Was this the way it was acquired? I don't think so. Let's assume that we followed this line of the parking lot, okay? Just let's say. And that kind of makes sense. It lines up. So I happen to have measured this already. It happens to be 3.1 degrees. I remember that. And lo and behold, there we go. So now everything is in, 3-dimensional or in 2D space. We actually know where we are in the real world, and we can go ahead and start acquiring things. Now, if I hadn't measured that 3.1 degrees, that's fine. I can go ahead and delete that. And I can say I'm going to add another point, and it's going to be north of the 49th, obviously, and hold on. And that's northern hemisphere, and 1, 2, 3, 6, and 25.8. Okay, so in this case, I'd measured another corner, and it worked it out for me. So all it's doing is taking the second latitude, longitude, and working out an angle to rotate the whole grid. So now I've got it all in the right coordinate space, and it's very simple to go ahead and do my processing and interpretation. All right, so that's all very well. Let's just ignore this and forget about it. I was sitting in a parking lot. Let's go back to our standard situation here. Right, well, this assumes that somebody started in the bottom and walked to the top and then for some reason, walk back to the bottom and, did all the lines in the same direction. Yeah, some surveys are like that, but most aren't, right? Most will have you walking from one direction up to the other and then starting a new file and going down in the other direction. Well, how do we account for that? Very simple. Let's say that we did that here. So that means every second line, in this case, the even lines are going to be flipped around. But what happens here? Wait a minute. Well, we don't know where the next line started. So we need to tell it, did you start at what level? Did it start at 60 meters? So let's just say it started at the reverse distance. It started at a distance of, 56 meters, right? So, well, okay, it should have been more, but whatever. Let's call it 58 meters then. So let's pretend that we had a baseline here that was 0, and somebody measured in another line here, which is 58, and each profile went back and forth. And now, take a look at this. So if you look at the line colors, it does show that our first line started here, went up here. But then we switched directions and started green here and finished red here. But all of the profiles are now shown in the same direction. So if we went and clicked on any of these, we can see the direction that we're going in, right? So whatever profile we show, the direction's always the same. Okay, so that's fine. That's pretty easy. That's how we reverse directions. Let's go back to our normal situation here. So another way we can do this is we can trim data. So let's say that each of these is, say 58 meters. The top of it was all garbage, right? I didn't actually want to show that. So I want to trim everything after, 55 meters. Let's go ahead and do that. Now every profile is perfectly 55 meters. We've just killed everything from 55 to 58 if you want to do that. Okay, so that's one way of making a perfectly rectangular grid, for example. All of this has been assuming that we know the trace spacing because we're using an odometer. Now, odometers are a little tricky, right? The optical encoders in an odometer work extremely well and they're incredibly accurate at counting. What isn't very accurate is all the mechanical components around them. So there's always a bit of slip in the gears. There's the belt drive system that never, is perfectly engaged. And of course, the wheels themselves experience slips and all sorts of things. So your odometer is accurate to a degree, but there's always some issues with the odometer generally. So how do we deal with that? Well, the first thing is if you happen to know that the odometer is always, 2% off, then you can add a separation multiplier right there and say, well, just add 2% or subtract 2% from whatever my odometer setting is, if you happen to know that. But there's other ways of doing this. So we can actually declare what the trace separation should be. So we could say, yeah, let's, I guess the odometer said it was, 1 centimeter. Well, no, I want it to be 2 centimeters. And now the trace separation is 2 centimeters. By the same accord, we can do trace density. Every 2 centimeters, actually a trace is, 50 traces per meter. So that's another way of stating that. We can force the profile length. We can say, you know what, we believe absolutely certain every profile is, 58 meters or 57 meters. And regardless of what the odometer says, it might have slipped. We're just going to force every profile to 58 meters or 57 meters. We can do that. The next thing is we can use markers. Now markers are rather interesting. Let me go ahead and delete these. Okay, so where's our, right. Okay, so if I look at this, show markers, let me go back to embedded trace separation. Take a look at this. So, pretty much every radar manufacturer, with the exception of a couple, allow you to enter markers, of course. And markers are very important. You can mark a fire hydrant, a pipe, or whatever you need to do. But you can use those markers as fiducial marks. And if you do that, then we take those in. We read them in from all manufacturers. And what's happened here, for example, is the user, let's assume, has established a baseline right here where they've pressed the button, the marker button on the console. And then this is their finish line. They've pressed another marker button there. And the markers turn up as these little red dots, okay? So, and we can even see the markers in the profiles themselves as red lines. Okay, So let's go back to these markers. What can we do with this? Well, let's say that we spray painted a line on the ground and said that was my start line and this is my finish line. And no matter what happens, I want to trim everything from marker to marker. So what we can do is we can actually say, yep, we have markers in here. We can add a marker. The first one is at 0 meters. The next one is at, I don't know, 48 meters. And now everything fits between those markers only, right? So everything beyond the markers has been trimmed off and everything before the markers have been trimmed off. So that's another way of getting your grids correct. If you can't perfectly start the wheel or whatever at the right point, you can use a marker, and as long as you know that that marker separation is 48 meters or whatever, then we can work within those bounds as well. Okay. Now, again, these are relatively simple, straightforward ways of doing things. But what if you have a situation where, let's say, for example, there's a light stand in the middle, or there's, let's go ahead and give it a, oh, well, my trace separation's wrong now. There's a light stand, for example, there's something in the way, or it's a very complex site. Well, for example, you may have been able to collect RTK data that states the start and end position of each GPR profile. That happens quite a bit in Europe, it seems, where they don't use GPS live being fed into the radar itself. They'll do straight line surveys, but with a start and end position. Well, we can deal with that too. So what we'll do is we'll go manual start end, and we'll go edit coordinates, and we'll go ahead and upload. Here we go. Okay, so there's two ways of doing this. The first one is if we had one file, this is an Excel spreadsheet, or it could be a CV, a comma separated file. Let's say that we have a file that looks like this. So this is an X position, a starting X, a starting Y, an ending X, and an ending Y. So we'll go ahead and say this is X, Y. It's already selected. This is X and Y again. Okay, oh, sorry. Start and end position. There we go. So X1 and then X2 and Y2. My mistake. All right. And then this last column lists the actual profile name. Now, the profile name must match exactly the file that's being uploaded, right? So if there's an underscore or whatever character, you need to replicate that. If you don't get it perfectly, that's okay. You can just confirm here and pick, well, okay, profile 1 is profile 1, or profile 2 is profile 2. And that works as well. So this will go ahead and position everything based on the start end positions, right? Another way of doing it is if you're using a total station, quite often it'll spit out just one coordinate pair per line on a spreadsheet. And it's a real pain to try and move those every second row up to the columns. So we can still deal with that. That's fine. That's just as easy. We'll go ahead and do 1 point per row. And in here we're saying, yep, that's the A column is X, the B column is Y. And we're going to say, well, this is the profile 1 and it's the start. This is profile 1 and it's the end, and so on. This is profile 2, start, profile 3, end. And you can declare it that way as well. It does the exact same thing. So that enables us to bring in very complex data sets that could have lines in all sorts of directions in really complicated grid patterns. Okay, that's all very well. Now, what we've been talking about thus far is, in general, except for these start and end coordinates, lines that work in one direction. But of course, we work in two directions, right? We want to pick up utilities going in two directions generally. So what do we do about that? And that's what we were talking about, folders. So let's go to another project. Again, I've already uploaded this data, and we'll call it bidirectional grid. Okay, so let's see what happens here. What I've done is I've uploaded some GSSI data into a folder called X, and you can see here that it goes from profile number 1 down to 79. And then my Y files go from, I guess, 92 to 170. I might be missing something in there, but that's fine. All right, so what do we do with this? Again, let's not worry about velocity and locations and all that. That's fine. So if we go into my positioning tab here, I do have a line pattern. Oh, I've already set this up actually. And what we can see here is that we have a profile separation of, well, 0. So, well, I'll see what I've done already. I do have a line pattern here, and I've already set it to, I guess that's 1 foot, isn't it? Yeah, it's a 1 foot. So my Y files seem to go this way, and they're 1 foot separated starting here, and that's, yep, 92 and up to 170 here. That's great. But where's all my X's? Well, they're all tucked down here because I haven't given them a separation. And in this case, what are we doing here? Well, we're going to do feet, and we're actually going to do a negative 1 foot. So again, starting down here, moving upwards. And we'll display that in a second. Now I actually don't know if these are the correct values, but oops. Look what I've done. My Y should be at 90 degrees. Okay, so yeah, I probably got those separations wrong. Right, well, I'm sure the grid looks a little bit better than that in real life, but you get the idea. So one of the folders will go at 90 degrees, one will go at 0 degrees. You add your trace separation, and now everything's in the right place. So again, and here we can go back and forth. So let's assume that every second one was reversed, for example, and it's 25. Let's say the reverse distance was 25 meters. I'm guessing here. So in this case, what we're going to do is reverse the X values here. And yep, there you go. So see what see the colors here. In fact, let's just turn off the Y files for now. So I can just turn off a folder very easily and ignore all the Ys. So yep, the profiles, let's say, started down here. That was a short one. Then he went up here and back this way. But no matter which way we look at this data, which way it was collected, we're always looking at it from left to right and from bottom to top. So that's how we do bidirectional grids. Now, some manufacturers, specific to Malo and Senses and software, they have very good software packages, and they have some files which come along with their data sets that are designed for, Echo Project and Object Mapper. And we can read those files in as well and help us position everything. So let's go ahead and do that. So right here, let's set up, actually I haven't got it set up yet, that's great. I'm going to go into my Pulse Echo data, and I'm just going to drag and drop right in here. So what this is going to do is read in the file. Now this is a compressed file of Pulse Echo data, and it contains a grid. That's all it is. Again, we don't care about the data itself. We're interested in the positioning of the grid, and thankfully Pulse Echo does have everything nicely set up. So there it is, it's uploaded, and if we go into the positioning tab, we should see exactly that layout of the grid. So what we can tell right away is, well, I don't know where it started, but this line was acquired from here to here, but we're looking at it from, always in the right direction. So no matter what, if this one was acquired backwards, we look at it in the right direction. And of course, let's say for some reason we want to switch that around, we can go ahead and reverse it. That's fine. And now we're looking at it backwards, but there's really no reason you should have to do that. So that works very simply for any Echo project or Echo Mapper, I don't know what they call it, project file. The same thing for Object Mapper. Let's go ahead and I've already actually loaded these in. Very straightforward, but what we have to remember here is to drag the entire directory. There is a file called, I think, OBM. That's very important. That tells the software where to load everything else, where to load everything in. And here we are. So what we've seen here is that they've acquired data in alternate directions, but look at where the 0, 0 point is, right? It's somewhere here. That's the Malo baseline. So this lines everything up, and you can, again, go through each profile one by one and easily interpret and track underground utility, for example. So this is what we wanted to show you today. It is, we've tried to address every possible scenario for really complicated grids, but there's always going to be things out there that people do that we're not aware of. So we rely on you guys to give us feedback, and we'll incorporate your suggestions very quickly. I mean, some of the changes we've made and upgrades were just done in the last 10 days, particularly with showing the original direction of the walking direction compared to the direction that you view the data on the platform. And that was done very quickly at the request of a couple users. So we rely on you guys to give us suggestions and raise use case scenarios that we haven't thought of yet. So that's the webinar for today. Hopefully everything was straightforward. Of course, we're taking questions, and I see a couple of them there. So we'll be back in a second with the question period. All right, guys. Thanks for tuning in here. We have a bunch of questions here. Let's see here. So our first question is from John Cabers from Australia, who is asking, will we support MGA? So this is a question that we're getting quite a bit of. I understand that, particularly in the UK, as part of the pass requirements, everything's done in the Ordnance Survey GB, and the French have their own requirements, and Australia has theirs, and you'd like to work in your own national grids. Initially, Geolitix was set up to work specifically in UTM WGC84, but we understand that there are requirements. So the intent is, in perhaps the next couple months, I don't want to put a timeline on it, that ideally what we'd like to do is support all of the EPSG grids and projections, right? So for every known projection, that shouldn't be very hard to do. There's a few things that we need to change, but eventually the answer is yes, we will support MGA and GDA, although I'm pretty sure MGA is very close to UTM anyway. For the time being, you can export your files in UTM and convert them in any other GIS software if you have access to that. And I think there's even some conversion tools online that are free to convert DXF files. Now, Helen's asked, let's see here. Oh, well, is there a non-cloud, so a PC-based version of Geolitix? No, there isn't. Geolitix was built entirely to harness the power of the cloud, right? It's not just speed, but the concept of collaboration. There's many advantages of doing things in the cloud. However, we have been contacted in the last 2 months since launch by a few government agencies, not just American governments, and a few military organizations that do have very strong restrictions on cloud, or simply are firewalled and they can't get to a cloud server. Helen, what I'd like you to do is perhaps contact us directly at Geolitix, the support@geolitix.com, or you can find my email somewhere. And let's have a conversation about that. I'm not saying it's never going to happen. There apparently is a very specific need for that for certain government agencies. And if the need is there, it isn't something that's entirely impossible. We recognize your problem, and let's see if we can come up with a solution that works for everyone. Let's see here. Hi, Alex. Okay. Right. I guess there's no other questions, and I didn't expect there to be a lot of questions with this webinar. It's a fairly straightforward one. What we really wanted to do is talk about, how grids work and understanding how we position things, because that's so important with GPR processing. I'd like everybody, if possible, there'll be a link to sign up for the next one, and that'll be a bit more exciting. We'll go through all the processing steps for GPR data, and we'll hold that in about 3 weeks. So we hope to see you guys all there. If there's no other questions, we'll sign off. Thanks so much for attending.